Now, in this part of the lecture, we'll be talking about the control of the glomerular filtration rate. So it is also called as the GFR. So since the amount of the salt and the water which is passing into the Bowman's capsule, it is more than 100 times greater than the amount appearing in the urine. So as we have discussed in the earlier lectures that near to 200 liters of filtrate is produced per day, but the urine which is going out, it is just 1 to 1.5 liters. So the filtrate which is produced per day is due to the glomerular filtration rate, and that is near to 100 times greater than the amount of the urine. So the large changes in the GFR could result in the disruption of the salt and the water balance. So if you have more of the GFR, there can be more of the filtrate produced in the nephrons, and if you have less of you can say the GFR, you will be having a less urine produced or the less filtrate produced. Now, this GFR, it is also having some of its impact on the reabsorption and the secretion mechanisms. Now, in the mammalian kidneys, the renal blood, it flows relatively at constant, you can say, volumes in spite of large changes in the systemic blood pressure. So what happens that if you are taking more of the salt, your blood pressure may rise to some extent, and that may affect the GFR or the glomerular filtration rate. The renal blood flow, it is again important in the time or you can say the rate of this GFR is dependent upon the blood flow. So it is actually the tuning the rate of the flow and pressure of the blood entering into the glomerular apparatus. So there are many, you can say, mechanisms which are checking the flow of the blood into the glomeruli of the nephrons, and they are playing a major role in the determination of the GFRs. So if more of the blood is entering into the glomerulus, there can be more of the GFR. And if you have some vasoconstriction in the efferent part of the nephron, then you can have more of the GFR again. So students, if I take the diagram of a nephron, and then I think you will be very much clear about the GFR. So here I'm again taking this particular diagram for giving you a concept that what are the factors which are affecting the GFR. Now what is the glomerular filtration rate? It is the rate at which the filtrate is produced into the Bowman's capsule, you can say in a unit time. Now if more of the blood is coming from the efferent arteriole, if your blood pressure is high, so there can be more inflow. And here you can very well see the efferent arteriole is having a lower diameter as compared to the efferent arteriole. So that exerts a pressure in the glomerulus, and that will result in the filtration process. So if you have less of the diameter of this efferent arteriole, or there is some vasoconstriction over here, then you can have more of the filtration pressure. So that can increase the GFR in this particular nephron. So if you have the reverse kind of a thing, if you have vasodilation, so if the efferent arteriole, it dilates, so what will happen that there will be a low pressure in this particular area if it is dilating. So if you have low pressures, there will be less of the filtrate produced. So it will be having less of the GFR in this particular case. Now, in the fishes, it has been seen that the GFR is high in the fresh water, but it drops by about 90% when the fish is transferred to the seawater. That means If a particular fish is transported from the freshwater area to the seawater, the osmotic pressures of the body fluids, they change so much that the GFR can drop by 90% in that particular fish. So that's how the external medium can also affect the GFRs in particular animals. Now students, if I take this particular concept further, so an important factor contributing to the rate of the filtration is the rate of perfusion of the glomerular capillaries. Now this is again a very important histological kind of factor which is affecting the GFR. Now the rate, it depends strongly on the state of the constriction of the renal arterioles. So as we have previously discussed, that if there is a vasoconstriction, there can be increased BP. So if BP increases, the GFR may increase. And if there is vasodilation, so there can be low of the BP and low of the GFR. Now, if I further discuss this particular thing in the renal, you can say, nephron, the kidneys, they are receiving a nerve supply from the sympathetic nervous system. Now, it is innervating a particular system in the kidney which is called as the juxtaglomerular apparatus. Now, this is the apparatus which is very, very important in controlling the GFRs. So I'll be taking this particular system uh, in full length. We have discussed two types of nephrons in the previous lectures. So if I come to this particular diagram, so here you can see the two types of nephrons which are present over here. So first are the cortical nephrons which are present in the cortex of the kidney, and they have got short loops of Henle's. And here we have the second type which is called as the juxtamedullary nephrons. So why they are called as juxta? Juxta is referring to as the close. So they are close to the medulla. So here what is close to the medulla is the Bowman's and the glomerulus. The Bowman's capsule and the glomerulus, they are very close to the medulla. So that's why they are juxta to the medulla of the kidney. That's why they are named as juxtamedullary nephrons. And in these nephrons, I have told you earlier that there is an affinity of the distal convoluted tubule, which is present over here, with the renal, you can say, capsule, or with the Malpighian body. So this association, this closeness of DCT and the Bowman's capsule, this is making a particular system in these nephrons, the juxtamedullary nephrons, which is called as the juxtaglomerular apparatus. Now I am starting with this particular apparatus. In this particular diagram, it is first of all, I would like to share that this is a juxtamedullary kind of nephron. This is not a cortical nephron. As you can very well see that the renal corpuscle, first of all, it is very close to the medulla. Number two, it is having that particular association with the distal convoluted tubule. So as you can very well see, this is the distal convoluted tubule, or the DCT. This is the PCT, and this is the loop of the Henle. So this association is making a particular system which is called as juxtaglomerular apparatus. Now if I go for this particular system, here it has been written as the juxtaglomerular complex. Now this complex is present in this particular area. Now in the next diagram we'll be seeing that how the juxtaglomerular apparatus is likely to be seen in the microscope and what are present in this particular system. Now students, this is a particular diagram that you have to draw. This is showing the juxtaglomerular apparatus, and first of all I would like to give you the concept that what is present in this particular diagram. Now here you can very well see this is the Bowman's capsule, this is the glomerulus, and this is a tubule, this is a TS of the tubule of the distal end. So this is the distal tubule which is being cut and shown over here. So this is the TS of the DCT which has got association with the glomerulus. So here you may find two particular things. Number one, it is the macula densa, and second, they are the JGA cells. So I'll be taking this diagram again. Before this, I want to give you the components of the JGA system. Now if you go for the juxtaglomerular apparatus, it has got three things. Number one, it is the macula densa. Now macula densa, it is an extratubular tissue which is very close to the glomerulus. So as you can very well see here, it has been shown in red colored. So it is in intimate contact with the glomerulus and the distal convoluted tubule. Now, there are the second type of, you can say, cells which are present in this particular system, and they are the receptor cells and the secretory cells. So these two types of cells are making the JGA. Now here it has been written as both the types, they are the JGA cells, and these are present in the efferent arteriole. So as you can see in this particular diagram, so we have got the JGA cells over here, and it is containing these two types of cells, the receptor cells and the secretory cells. Now what happens in this particular system? Now what is the function of this particular system? Now if I give you some concept of the function, first of all we have to consider a particular situation. Now what is the situation? That if the salt concentration in the, you can say, the blood, it decreases. So what will happen? So there will be two things. You can write in your copy. The condition is that we have got number one, low plasma sodium content. So if we have low sodium levels, this system will operate in that particular condition. Number two, if the vessel pressure or the blood pressure, here we should say the vessel pressure because we are taking the efferent or afferent arteriole into account. So what is present over here is the second situation is low of the pressure. The first one was low plasma sodium levels. So as we have low of the sodium ions in the plasma of the blood, which are coming from this efferent arteriole, so it is sensed by the JGA cells. So as the blood is coming from this efferent arteriole and it is leaving the glomerulus through the efferent arteriole, if you have low of the sodium in this particular blood, it will be sensed by the sensory cells of the JGA. And the receptor cells, they are also helping in receiving that particular stimulus. So JGA cells will receive this particular stimulus, and these are the renal nerves which are giving an impulse to the brain, or to the you can say the nervous system. And what will happen, that the second part of the JGA, that is the secretory cells, they will secrete a particular compound which is called as a renin, RENIN. So in lieu of, or in the response to the low sodium levels and decreased pressure, what will be released by JGA cells? It is the renin. So this renin, it will go to the blood. It will be secreted into the blood by these particular secretory cells of the JG apparatus. Now when the renin, now it is going into the blood. Now what it will do, it will change a protein which is the alpha globulin protein, and this is already present in the blood. And I must give you this particular thing, that alpha globulin, it is secreted by the liver. So in the blood we already have this alpha globulin by the liver, secreted by the liver, and the renin which is secreted over here, it changes that alpha globulin protein into angiotensin 1 protein. So this is a mechanism that you have to write in your copy. So the first step is secretion of renin by the JGA cells, by the secretory cells of JGA. This renin will convert the alpha globulin into angiotensin 1. Now angiotensin 1 is a 10 residue peptide, and it is present now in the blood. Now this angiotensin 1, it is a 10 residue peptide, and out of these 10 residues, 10 peptides, 2 amino acids will be broken down by the converting enzyme, and this angiotensin 1 will be converted into angiotensin 2, which will be 8 peptide residue. So that means we have got angiotensin 1 converted into angiotensin 2 in the blood. Now this angiotensin 2 has got two fates. Number one, angiotensin 2 will result in the vasoconstriction of the blood vessels. So what will happen? The arterioles, they will constrict in the presence of angiotensin 2. So if they will constrict, what will increase? The blood pressure will increase. So if blood pressure is increased, the condition from which we had started of a low BP, that is countered, that is equilibrized. So this is the mechanism of angiotensin 2 by the vasoconstriction to increase the BP. Now angiotensin 2 can go for the second route also. So what it is doing, it stimulates the adrenal cortex. So the angiotensin 2, which was formed from angiotensin 1, it is stimulating the adrenal cortex, which in turn produces aldosterone. Now when aldosterone is produced in the blood, it increases the sodium reabsorption from the DCT. So as we have discussed it in the physiology of the nephron, so this aldosterone hormone, it is acting on the distal convoluted tubule, and it can increase the sodium absorption into the blood. So if sodium is increased in the blood, our condition of low plasma sodium, it is automatically matched up, and now a homeostatic mechanism will be developed inside the body. So that's how this particular system, which is called as the JGA system, it regulates, or it is a self-regulating kind of a mechanism, and it regulates the sodium levels in the body, and it also regulates the pressure or the vessel pressure inside the nephrons. So that was all about this particular system, how it works. So students, if I summarize this particular juxtaglomerular apparatus, so we have three types of cells in JGA. First are the macula densa, which is sensing that particular vasoconstriction or dilation. Next, we have the sensory cells of or the receptor cells of the JGA, and then we have the secretory cells which are secreting the renin into the blood. So this particular system is present in the arteriole, and when the blood it enters into the glomerulus, this system senses high or low plasma levels of sodium. Now when they are detected, they secrete renin in the response. That will convert the globulin into the angiotensin 1, then 2, then it can vasoconstrict the vessels, or it can go for the adrenal cortex, formation of aldosterone, and that will act on the DCT to increase the sodium absorption and ultimately increased blood pressures. So that was the basic mechanism of the JGA. Sometimes it is also referred to as the RAAS system. So it is referred to as the RAAS system. It is RAAS. So what is RAAS actually? This is the renin aldosterone angiotensin system, or I should say it is the renin angiotensin aldosterone system. So here we have, first of all, the renin component. This is a very basic component that is needed for achieving the high sodium levels. Second is the angiotensin, which is formed from the alpha globulin, which is a component from the liver. And second A is for the aldosterone, which is released by the adrenal cortex in response to the aldosterone, the angiotensin. Now the S is for the system. So this particular system is also increasing, or you can say it is maintaining the balance of the sodium in the body fluids. So students, with this we finish with the JGA system, and there is a control of the tubular reabsorption of the sodium by the help of the aldosterone that we have already discussed. If we go for the water reabsorption control, this is with the ADH, as we have already discussed in the nephron part or the physiology part. So ADH is also helping in water reabsorption, and the aldosterone is going for the reabsorption of the sodium. So I think, students, that was all about the nephron, and that was all about the physiology of the urine formation, that how the nephron is going for 3 or 4 stages, out of which a urine, or the final urine, is formed at the very end. So students, summarizing the whole mechanism of or the physiology of the nephron, this particular diagram will help you a lot. So if I go with the first process of reabsorption, so here we have that the sodium ions, they are going out. So you can very well see this is the sodium chloride, we have the potassium, water is coming out about 80% that we have discussed earlier. This is the bicarbonate ions. We can have glucose. Whole of the glucose will be reabsorbed. Many of the amino acids, they are coming out as a reabsorption, you can say, products. So then creatinine, antibiotics, diuretic, and uric acid, they are given inside this particular proximal convoluted tubule. So these may be some of the toxins which are modified by the liver with the help of those two compounds which we have discussed earlier in the tubular secretion. So if I go further, if I go for the loop of Henle, so here you can very well see that the first part, or you can say the descending limb, here we have some of the sodium chloride which is coming out, and this is a kind of reabsorption of sodium. We have the potassiums which is coming out, water is coming out to some extent. Then we have the magnesium and the calcium, they are also coming out of this particular descending limb of loop of Henle. Then here magnesium and calcium, they are also coming out. The most of the sodium chloride which is coming out actively, this is in the thick or ascending limb over here. So this is the basic, you can say, the principle behind the countercurrent system as we have discussed earlier. So the sodium chloride is coming out, that is making a gradient difference in this particular medullary part. Now if I go further of this loop of Henle, now we have the distal convoluted tubule. So here you can very well see that we have the sodium chloride, some of it is coming out, it is only 10%, and we have the calcium coming out, it is reabsorbed also. It is under the control of a particular hormone which is called as the PTH. So this hormone, we have not actually taken this particular part in nephron, as we were only concerned with the sodium and the chloride over there. But here, this is a very important hormone which is acting over here, is the aldosterone. So this is in connection with the sodium reabsorption. So this is on the distal convoluted tubule part. So some of the water is again coming out from this particular thing. If I go to the collecting tubule, the basic hormone that is acting here is the ADH. So this is the antidiuretic hormone we have already discussed in the previous sections. So some of the water is reabsorbed over here, and this is the major concentrating part in the nephron. So this is also called as the antidiuretic hormone. That's why it is controlling the reabsorption of the water in the collecting tubule. So students, you can draw this particular diagram in your paper for a complete physiology of the nephron. So with this, we finish with the structure of the kidney, which included the origin of the kidney, how the tubules they develop, what is the evolutionary process of development of the tubules. So then we have discussed some ducts in the archinephros, and then we talked about the structure of a typical mammalian kidney. Then we talked about the anatomy, then we talked about the physiology of the kidney, the excretory system as a whole, then we talked about the urine formation, the mechanism of urine formation, and then we had talked about the control of the pH, control of the ion secretions, control of ion reabsorption. So I hope that you have understood all the concepts, and that was all in this particular topic. Thank you.